So, in case h is a, we take h to be a growing function and then look at this padded SAT. So, this is not NP hard, it is not as hard as NP hard. The reason is that if it was, then a SAT instance psi is being reduced to a padded SAT instance, phi is 0, 1 to the phi h phi, and it can't be too big, so its size n to the c for constant c. Now, when you look at the size bound n to the c, you get that then phi has to be extremely small. So, in other words, what is happening is that psi of size n is being reduced to a much smaller SAT instance. So, which means that psi reduces to phi of size small o of n. So, which means that on repeating this, let us say around n times, many times, we get CNF tau of constant size. Right. So, psi will reduce to phi and then phi 2, phi 3 dot dot up to tau where tau will be constant size. So, then it will become a trivial problem to solve. So, which will mean that SAT is in P. Can that happen? Well, we have assumed P to be different from NP. So, that is a contradiction. Right. So, this contradiction means that SAT H is not NP hard. So, that finishes our first observation. So, padded SAT we have shown is not NP hard, and to prove Ladner's theorem, our intention is to show that SAT H is in NP minus P. So, we have shown it is not NP hard. Obviously it is in NP. The only thing remaining is it is not in P, right. So, can it happen that SAT H is in P? So, to deduce that SAT H is not in P, so this requires balance on the opposite side, right. So, we have shown in the previous observation that SAT H is not as hard as NP hard, but then it should also be not as easy as P. So, we have to make it slightly harder. So, for that H should be not too large, okay, it should be somehow small. So, we define H in a way so that it grows very slowly, first of all, and allows a diagonalization argument. Okay, so somewhere a Turing machine negation has to happen, and this will be a polynomial time Turing machine, negate the answer. So, let us define it that way. So, H of n is the smallest I such that for all x of length log n or less binary strings, mi accepts x in time I times x to the I, if and only if x is padded sat. Right, so this looks like a complicated definition, but all we are saying is that this I we are defining as each of n, where I is actually the exponent in the time complexity. Okay, time complexity of what? Of padded set. Right, so this is a kind of a cyclic definition. Padded set will be defined once we have H, but now we are using padded set to define H itself. But the reason it will be fine is because here we are using in length. Okay, so we are defining Hn by looking at the initial part of sat H, the strings which are very small. So this is a recursive definition. And if this mi doesn't exist, okay, this Turing machine descriptor also running in time x to the I, if it doesn't exist, then you just define Hn to be log n. So if there does not exist such an I, then define H of n to be log n. So either there is a Turing machine descriptor below log n, or you just call log n as your function. So either way, you see that Hn is expected to be a growing function, but very slowly growing. It's like log n, and it also will allow you diagonalization tricks, because it's actually using this Turing machine descriptor. Okay, Hn is kind of a Turing machine descriptor that solves padded sat in polynomial time. Well, I shouldn't say polynomial time, in yeah, this very small exponent like log n. So now Hn is computable in Hn is easy to compute. Let me just say that. Why? Again, because the strings involved are very small. They are only log n, so log n length, so their number is only n. So you can actually and the possibilities of I is also very small, so you can actually go over all these in an exhaustive way. Okay, I can be looked for exhaustively. So how many i's? So number of i's is log n times number of x's is 2 raised to log n and it's not really 2 raised to log n. Let me increase it a bit, times log n times time of mi. How much is that? Time of mi is roughly x to the I, right? So that is length is log n and exponent is at most log n. And then to solve SAT, because you want to check whether this x is in padded SAT. So SAT, so time complexity of SAT, let me just say that's 2 raised to log n again. So if you calculate this, this will come out to be n another n, just n square. It's smaller than n cube definitely. Okay, so it's subcubic, almost quadratic time. You can compute h of n. It's easy to compute. So now we can show that SAT h is not in P. For this h, okay, with this definition of h, the padded SAT is not in polynomial time. And once we have shown that, if we can show that h tends to infinity, then with the first observation we will have a complete proof of our theorem, Ladner's theorem. So let's first show that SAT h is not in P. Let me call it claim 1. It's it's this for this h, SAT h is not in P. Suppose it is. So suppose Turing machine M solves SAT h in time c n to the c, obviously constant c. So then what do you do? So as is now usual with the diagonalization proofs, we'll pick a descriptor of M, let's say J, and argue with that. So pick descriptor J, which is a number larger than C, such that M is Mj. Pick a large enough descriptor of this Turing machine, and now let us go through this definition of H. So what we have is that Mj decides SAT H in less than n to the j time. Which means that by the definition of H, Hn has to be less than equal to j. Right, that's how we define H. SAT solver, its descriptor should be j and the exponent should also be less than j. Or in fact, we give more, it's the same descriptor. Descriptor should be in the exponent, so x to the I. So by that, Hn is less than equal to j. And less than equal to j for all n greater than 2 raised to j, for large enough n, right? That was in the definition. For large enough n, this happens. Each of n is less than equal to j. So this means that SAT H is just SAT padded with how many ones? 1 to the n to the j. That's all there is to SAT H. It's just SAT instances, and then you are padding with these at most, in fact, n to the j ones. And since j is a constant, this is just a polynomial blow up in the complexity. So if you can solve sat h, then you can solve sat. So you get that sat is in P, right, which is a contradiction, which means that sat h is not in P to begin with, right. So this definition of h is good. It puts sat h, padded sat, outside P, but then it could be, it's possible that it's very hard, maybe it's NP hard. So we have to go back, right. We would know that sat, padded sat is not NP hard if we can show that h is growing. So does this definition give us an h that grows? That's our claim 2. It does. So Hn tends to infinity. How do you show that h grows? See, by the definition of h, growing would mean that in some sense sat h should not have a polytime algorithm, right? So this again falls back on claim 1. So actually claim 1 gives you claim 2. So sat h not in P implies that for all I there exists an x such that Mi cannot decide whether x is in padded sat or not in time since there is no polynomial algorithm, so there cannot be a machine which can solve it in time x to the I for any constant. There will always be a string which will take more, require more, right, more time. So what does that mean? It means that Hn cannot be I. So this means that Hn is not equal to I for all n greater than this x. So let me use maybe a descriptor here, subscript here. So let's call this x sub I. And for this x sub I we get okay. So taking n bigger than that disallows Hn to be I. In fact, it disallows. It means that Hn has to be bigger than this. Hn can't be I or less. So this means that Hn takes a value I only for finitely many n. Right. So because for any I after a certain point Hn cannot be I, it will be bigger, which means that Hn tends to infinity. Maybe I use this not equal to, that's the simplest thing. You deduce from the previous statement. Yeah, and then which means that Hn tends to infinity. Okay, so that's claim 2. and hence, so by claims 1 and 2, we have a polytime function h such that sat h is in NP, not in P, and not NP hard. Right, all these properties are now true for this H, and this H is easy to compute. That was also important actually. That's important to put sat H in NP actually. I should have maybe set it here. Okay, since H is not a complicated function, so given an input, you can easily check. In polynomial time, you can check. And yeah, so it's in NP, it's not in P, and because Hn tends to infinity, it's not NP hard. That finishes Ladner's theorem. So now, once we have seen all these proofs, you may wonder if diagonalization is so smart, such a clever technique, can it prove P different from NP? Can it prove P different from NP? And let me say, can it alone prove without using any other innovation? Okay, maybe if you use many other techniques, then it helps, but just using diagonalization type of arguments, will it suffice? Will it be strong enough to show P not equal to NP? And so to answer this, we will study oracles. So this leads us to the concept of oracle. So oracle and relativizing proofs. So one direct motivation for oracles is suppose you have solved a hard problem like SAT or even HALT. By using an alien machine. Okay, some alien came from some other planet with a very powerful device that humans have not built yet, which can solve a halting problem or satisfiability, which is much easier than halting problem. Let's say it solves it in polynomial time. So which problems can you now solve? Okay, using that alien device, what other problems could you solve? So this actually gives you a new way of defining complexity classes. So this yields new complexity classes, and let's see the definition. So we call Turing machine O, Turing machine M, an oracle Turing machine using a language O. If M has 3 special states, so a query state, yes and no. So what will happen is that the way Turing machine can use an oracle, for example this alien device, is it will put on the work tape the string y which it wants O to solve, oracle to solve, and go to state Q query. The oracle will immediately solve it, and then the Turing machine will either go to state Q yes or Q no. Okay, if the string y is a yes string, then yes state, otherwise no state. So in one step the problem is solved, no matter how hard, using this oracle. In fact, we can introduce an oracle tape, so special oracle tape. In addition to input tape, work tape, and this is the third oracle tape, such that M enters or if M enters in state Q query, with y on oracle tape, then in the next step the state is Q yes, respectively Q no, if y is in O, respectively y is not in O. Okay. So we'll develop this more next time.